Hi, everybody. Welcome back to the afternoon session. Hi to all our online participants. Please write your questions on the chat and I'll be monitoring it. It's a pleasure to have Niao He, who's also one of the co-organizers of this workshop, start this afternoon session.
Yeah, thanks for the introduction, and yes, welcome back. So I think we have already heard a lot of talks on Minimax optimization. Unfortunately, to those of you are already bored with Minimax optimization, this will again be Minimax optimization. But luckily, I think on the good news side, this is perhaps also the last talk about Minimax optimization for the workshop. I think for the next two talks and also the talks tomorrow will be more on the learning side and also adversarial approaches. So I think in the last in this week we have already heard lots of stories about new exciting results about either classical Minimax optimization algorithms or newly developed algorithms. And a kind of a common phenomenon oftentimes we see is like those simple algorithms like gradient descent ascent or extra gradient methods may not always be the best choice of algorithm, right? They might not necessarily give you the best performance. Whereas algorithms that gives you better performance or improved bounds oftentimes require much more tweaks and also like oftentimes needs to go to multiple loop structure. So in this talk, I was trying to really answer the question like, is there hope to get simple single loop algorithms that achieve potentially even better performance bounds than those multiple loop algorithms? And in this talk, I'm going to give you kind of two very cute results, I'd say, like that closes some of the gap in the literature. And I should say, most of the part of this talk is based on this very recent work that is joined with two of my very amazing collaborators, Kiran and Siwam. Kiran is a research scientist from Amazon, and Siwam is a professor at the University of Washington. And this work was just being accepted to AI Stats in 2022. And if I have time, I will discuss another work which has a very similar flavor, but in the stochastic regime. Okay. All right. So I think whenever we talk about complexity of Minimax optimization, we want to really be careful that oftentimes the complexity is related to three components, right? First of all, what is the specific problem class that we're talking about? And this is oftentimes specified by the like smoothness, the convexity parameters, right? And then it's also the other element is really what are the information we are getting from those objectives or from the problems, right? Whether it is first order, zero order, or whether it is black box or white box oracles. And then it's also what is the notion of solution concepts here, right? Whether it is the Nash equilibrium or it is the first order Nash equilibrium, or maybe it's some other notion of equilibrium, right? So all of these were these two different complexity results, right? And by complexity results, oftentimes we look at both on the lower bound side and also on the upper bound side. And by upper bound, we mean that we want to find out what is the least amount of what is the number of oracles you need at most, right, to solve all problems in this problem class by a given algorithm. And by lower bound, we mean that we want to identify what is the least amount of efforts you need to pay for all the problems in this problem class, right, in the worst case. So, and ideally, we want to find some algorithm that's optimal in the sense that it achieves this lower complexity bound, okay? And in this talk, I will mainly be restricted to this very generic smooth Minimax optimization problem that was characterized by a number of parameters here, right? Those L corresponds to the smoothness and mu corresponds to the strong convexity. So by smoothness here, I have Lx, which is kind of the smoothness of the X component of the gradient, right? There is Ly, which corresponds to the Lipschitz of the Y component of the gradient, right? There is Lxy, which is the gradient, the Y component of the gradient. What is the Lipschitz in terms of the X space, right? So basically, you can view these constants as basically just the L2 norms of your different blocks of your Hessian matrix, right? If your function phi is twice differentiable. We can also define what is the strong convexity, right, for the X component and strong convexity for the Y component. Okay. And we know that if mu are greater than 0, those are strongly convex. Equal to 0, this means it's convex. Less than 0, it's weakly convex. Okay, and those are those are non-convex settings. So, and we know that most of the talks, right, we see are really dividing, problems into different regimes based on the convexity, right? There is extensive literature on convex, concave, strongly convex, strongly concave settings. More recently, there are more and more work on these other settings, which are, some kind of in between this convex, concave, and non-convex, non-concave, right? And you can see that in all these new settings, those are really settings where there is some asymmetry between the two players, X and the Y, right? The convexity parameters are different, right? Whereas in the classical ones, oftentimes we say that it's kind of more symmetric, right? They're either both convex or both strongly convex, okay? And there's, as you can see, there's not much really division here about the Lipschitz smoothness, which is actually equally important as convexity. So as I said, like most of the classic settings, we look at the cases, let's say we treat kind of a uniform bound for all of those Lipschitz constants, Lx, Ly, Lxy, as let's say just all of them are equal to L or bounded by L, right? And then the convexity, let's say they're also the same, mu x equal to mu y, right? And all of these are oftentimes captured by variation inequalities, right? This was already, I think Ineda gave a very good kind of tutorial or like summary of variation inequalities this morning, right? You can basically say that we're just interested in this operator F, right? Which is mu strongly convex or mu strongly monotone and L Lipschitz, right? It doesn't really differentiate those different Lipschitz constants for different components, X and Y, right? So, and we already know of those kind of stories about the lower bound there, right? For these general variation inequalities with monotonicity and the Lipschitzness. And then we also already heard again and again what are the optimal first order algorithms that can achieve these lower bound complexities. We talked a lot about extra gradient, right? Optimistic GDA. There are also many other variations or many other algorithms that provide the same complexity bounds. So what I want to talk about is what happens if we look at the cases where those Lipschitz are different or those strong convexity terms are different, right? So because in most cases and also in practice, maybe those, as we see also before, right? Your strong convexity parameters, mu x, mu y, in many cases are not necessarily in a symmetric form, right? Similarly for the Lipschitz smoothness terms. So what do we know about the lower complexity bound in this case? So the result was only established, I think there was explicit description that was given only like a few years ago by Shudong Zhang and the co-authors, right? They shown that this is, in the case, let's say your both X and Y are strongly convex or strongly concave, then you can show that you get linear convergence, and this is the total number of complexity you need. Okay, so there is this condition number, which is the square root of Lx over mu x, right? Plus this Lxy square divided by the product of mu x, mu y, and then there is this other term from the Y component side. So this result, like if you look at it, is also kind of intuitive, right? Like if you think about, let's say, this very special class of problems, which is also very general, right? So if you say you have three components in this phi of xy, right? There is the bilinear structure, which is fairly common. And then there was those separable functions, fx and the hy, right? And let's say those two are strongly convex, okay? And then you have bilinear structure here. So it's kind of intuitive that, right, if you don't have these two terms, or if those two terms are very simple, let's say fx and hy are very simple terms, which you can easily compute their proximal operators, then you can expect that you will get some bound like this, right? You will get Lxy over square root of mu x mu y, right? In the complexity, if you run, say, proximal point algorithm, or if you run just, extra gradient method. if you don't have these two terms, right? If you just have this fx, right? You have to minimize fx, right? This is basically the lower bound for smooth minimization. If you only have this, then you have that, right? So that's why this is kind of very intuitive. That is, this is what you're expecting, right? To be the lower bound. Okay, and I should mention that in fact, the hard instance that was used to construct this lower bound is fairly common, right? It's just a quadratic problem where FH are quadratic and have this bilinear structure, right? So it's not like really a lower bound for some pathological hard instances, right? This is just, even for the most typical problem, you would expect that you have such kind of lower bound. So what do we know on the upper bound side, right? So of course, like you might just pick up your favorites, let's say extra gradient or OGDA method, and you immediately see that the complexity you get is basically going to be the, again, you get linear convergence, right? But the condition number here is going to be the maximum of the Lipschitz constant you had divided by minimum of your strong convexity of two components. Yes? Sure.
Ramon was constructed with a quadratic example. Do you know if it's a finite dimensional quadratic example or infinite dimensional? Because
I think it's finite dimension, yeah.
Because I know that like for the Nesterov, at least on the minimization, so it's not that easy.
So you need your dimension to maybe grow with your number of iterations. So coming back to extra gradient type of methods, right? So this is basically what you will get as the complexity. And you can see that it's very different. That actually is much worse than this lower bound. And if you use just gradient descent ascent without extra gradient or this optimism, you get the square of this condition number, right? So this is better than just doing gradient descent ascent. So if you have been to my talk like 2 weeks ago at the seminar, then you see that we have provided some like simple acceleration of extra gradient or OGDA by just combining it with the catalyst acceleration framework. You can immediately boost this convergence to L divided by square root of mu x mu y, right? So this square root of mu x mu y, this is better than just taking the minimum there. And that is like a simple two-loop algorithm you can use. And that you can see that if your L, right, is the same among all of those components, then this is indeed the optimal you can shoot for, right? Based on the lower bound, this is actually the best you can shoot for if your L are uniform among different components. If those L are not uniformly among those components, then this, of course, is not optimal one, right? At least it's very far away from the lower bound we see before, because in the lower bound, you only have L, X, Y here in this dominant term here. So there was one work that coming out, I think maybe last year by Cohen and Aaron and Kevin, I think. And they shown that if you just rebalancing the kind of the distance generating function using extra gradient method or mirror prox algorithm, you actually will be able to get an improved complexity bound, which looks like this. Right? If you look at this term, you can see that they basically get a kind of the optimal term here in terms of the dependence on this coupling term Lxy, right, divided by this mu x mu y. But it's not optimal in terms of these two terms, right? You can see that if Lx and Ly are very large, then this is much worse than the lower bound we see before. Right, so the lower bound is here. Sorry, I should have put it in the other slide. So the square root of these three terms. Okay. So lastly, I think in the New Rift 2020, there was a paper called the Proximal Best Response that provide this algorithm, which is a very sophisticated for-loop algorithm that combines all kinds of techniques like exact proximal point algorithm, like best response, alternating updates, and then like all those, like just throw everything together. And then they're able to achieve this bound here, which is the best known bound, I think, in the literature so far, right? And you can see that it's very close to the lower bound, except that this middle term here is Lxy times L. L is the maximum among of your Lipschitz constants. right? In the lower bound, we have Lxy squared, okay? And you can see that if Lxy is, let's say if Lxy is much smaller than L, right, then this is much worse than the lower bound we see before. If Lxy is kind of dominating, like it's very large, then this is more or less comparable to the lower bound, right? So this bound is kind of more or less very close, but it's still, like as the author pointed out, there is still a very significant gap if Lxy is very small, or your mu x mu y are very small. Okay. So of course the straightforward question here is, can we close this gap here, right? And also very interesting to see, can we achieve this? Can we close this gap by just using a very simple single loop algorithm instead of having to go through this 4-loop, 5-loop algorithms to achieve the optimality there? So that is kind of the goal of the talk. So maybe I should stop here and see if you have any idea, like, do you think there is any hope that we can actually close this gap, or maybe the lower bound is a lot tight, or maybe like you won't be able to achieve it with single loop? Yes.
Actually, I would like to ask the question more general to the audience. For example, has anyone tried to do SOS for the primal gap from the Primal-Dual gap to understand the matter? Is there any way to use SOS to understand if the gap, if the constant, even for a class extra gradient algorithm, to do that?
So that's the question for Yang, right?
Yeah, I don't know.
Is the expert SOS?
I am inspired by you.
I guess the point Niao made is that extra gradient, I mean, I guess he's saying like not look at it as a variation in the quality, but try to play the step sizes of something.
Yes.
Yeah, I think that's good.
So I think that's a good question. Like those SOS analysis might give you a hint on, how to choose the right step size, or how to choose the right algorithm. So here, like our approach here is actually, our idea here is really fairly simple, right? Let me just maybe just first give you the spoiler of, and also actually let me just first motivate. Why do we even care about achieving this, close this gap and achieve the exact optimality, right? Because it feels like, the gap is really small. Why do we even care about, closing this tiny gap here? And I think the answer to this is really already given by many of the talks from yesterday, like in Mason's talk. I think he talked about, if you look at these other settings, right, when you have non-convex concave settings, oftentimes you want to add a small regularization, right, to the objective, make it strongly convex, strongly concave. And those regularizations are basically this mu here, right? Those are very small, like of order epsilon or even smaller, right? So you really want to get the optimal dependence here with condition number, so that you will be able to translate it to other settings to get the optimal dependence on epsilon, right? So it's crucial here. And I think yesterday, Sohail also gave a talk on talking about like how the Lipschitzness actually corresponds to different robustness, right? So it's really important to get the tight bound on the Lipschitz so that you can get better robustness guarantees as well, right? And why do we care about designing a single loop algorithm? Like what's so bad with multiple loop algorithms? Of course, everyone likes simple algorithms that are elegant, right? So I think the answer to that is also, like, as I alluded before in my other talk, that if you get a algorithm, an optimal algorithm for the strongly convex, strongly concave problems, you can easily combine it with the catalyst acceleration or other acceleration framework to get optimal, potentially optimal or near optimal bounds for those many other settings, right? So if you have a single loop algorithm here, then you will be able to just achieve very good, better algorithms with good complexity guarantees for all these other settings with just at most 2 loop, right? Okay. So how should we achieve this, right? And do we have an answer to that? And the answer to the previous two questions I had is we have some positive, right? We are able to kind of close the gap for at least this class of bilinearly coupled min-max optimization problem. As I mentioned earlier, this class of problems is exactly like the class of problems where this lower bound was constructed from, right? So this is not just a very restricted class. And the idea is also very simple. We use it based on the Primal-Dual lifting, which I will discuss kind of what is the details very soon. Of course, you might be wondering, like, can we really relax this, right? Can we close the gap for even more general functions that does not limit it to this bilinear structure, right? And the answer, I think, partly is yes. And there was a recent work that was released on arXiv by, I think, Yu Jia, who is also here, and then Aaron and also Kevin, that has shown that you can actually use a similar idea and some other analysis. You can show that you can close the gap for this more general separable min-max optimization problems. That nearly matches with the lower bound. There was a tiny bit difference, I think. So lastly, I want to mention that these settings that we're looking at, this bilinear min-max optimization, you might feel like, okay, isn't this has been already well studied, right? In the literature, it has been lots of this Primal-Dual and all kinds of algorithms to solve it. So I want to mention there are several key differences, right? So first of all, in most of the literature, when you look at this type of structures, they look at the cases where your f function and h function are simple functions where you can easily compute their proximal operators. Right, but here we assume that you only have first order access to f and h. You cannot compute the proximal operators. Right, there are other methods that maybe assume only one of them is proximal friendly. I think there is another paper, I think, that shows that is also gets linear convergence for problems. Let's say only one part is strongly convex, the other one is not strongly convex, but A is full rank. All of these are kind of related, but those are not really fit into the problem class we consider here. Okay. So how do we come up with some algorithm that gets the best condition number, right? So what is the idea here? So the idea is basically that if you wanted to kind of exploit fully the structure here, right? There is this bilinear structure, there is a smoothness structure here, right? We want to think about and say, what is the optimal algorithm that can leverage this bilinear structure? There are many of them there, right? One method is like, there's extra gradient, there's Primal-Dual, and many others, right? What are the algorithms that leverage the smoothness to its best, right? Those are like accelerated gradient methods, right? Of those. So it came to like a simple idea that came to us is like, you can actually use just the Primal-Dual method to handle this bilinear term with optimal guarantees. You can use also Primal-Dual algorithm to handle these smooth terms with optimal guarantee. And then if you just apply Primal-Dual, then you're good to go. Right, so let me just be a bit more detailed about that. And before that, I want to mention that the simplest or the most prominent examples of this type of problem is just quadratic minimax problems, which actually occur pervasively in the literature. Like there's like if you have a matrix game, but you have some quadratic constraints, right? You can reformulate this way. If you look at the robust least square, it's also like exactly this type of form. If you look at, say, just the policy evaluation objective, like the minimize the mean square projected Bellman error, is exactly like gives you this type of objective when you use linear function approximation. So it's not really just a limited problem class here. Okay, so what is the inspiration here we got to solve this problem? So the first idea, the first thing, as I said, we want to look at this bilinear structure and see how we can handle it. And we know in the literature, right, if you have bilinear structure and if you have some function, let's say I'm using capital F and capital H here, let's say those are strongly convex, and those are functions that you can easily compute their proximal operators, right? I call them proximal friendly here. So one way, of course, to solve this problem, as we all know, is you can use the Chambly-Pock Primal-Dual method, right? You take this extrapolation step for y, right? And then you do this bilinear term plus some Bregman divergence, and this function f, you just keep it intact here when you minimize this, right? You do the same for y, right? Alternatively. So this is just the Primal-Dual method. You can actually view this Primal-Dual algorithm as just an approximation, again, as proximal point algorithm, just like extra gradient or optimistic gradient descent ascent, right? If you apply proximal point algorithm to this problem, that will exactly give you these two updates, except that you're not going to have y tilde here, you have yt plus 1. And you have an explicit update here. And here, Primal-Dual method basically says instead of using yt plus 1, which you cannot compute, you replace it by this extrapolated yt plus 1 tilde, right? That's it. And you can just follow the analysis of proximal point algorithm and can easily analyze this Primal-Dual and get this iteration complexity, okay, for solving this problem, which, as I said, is optimal for solving this class of problems. Okay. So all of these are very classical, right? This has been well known. So what about the smooth minimization, like f of x, this part, right? If you want to minimize f of x, we know that the best algorithm to solve it is Neserov's accelerated gradient descent method. And that also has a Primal-Dual perspective. So let me elaborate that. Right, if you want to minimize f of x, this is equivalent. Let's say f is mu strongly convex. This is equal to minimize. We decompose it into terms, right? There is a quadratic term plus fx minus this quadratic term here, which I denote as f underline here. And this f underline here is convex, right? You can rewrite it as using its Fenchel dual, right? So you can rewrite this objective just f underline by maximize over mu of this inner product minus this Fenchel dual, right? So you have this min-max reformulation. If you look at this min-max reformulation, it's exactly the same form as what I discussed before, right? You have simple term here, another simple term here, a bilinear structure here. You can solve it by Primal-Dual algorithm, right? Just apply the previous Primal-Dual algorithm to solve this. This is what you will get, okay? And you can see that in this case, your mu x, right, is mu. And your bilinear term matrix A there is just identity. So your Lipschitz constant Lxy is equal to 1, okay? And your mu y is going to be the strong convexity of this term, Fenchel dual, right? You know that f is L smooth, right? Your f underline here is L minus mu smooth, right? This Fenchel dual is strongly convex of parameter inverse of 1 L minus mu, right? So you plug in this into the previous bound we know here, right? Your norm of A is just 1, mu x is mu y is L minus mu inverse. You get automatically the iteration complexity, which is exactly the optimal rate you would be achieved by accelerated gradient descent. Okay. And in fact, when you look at this algorithm, you might say, okay, how am I going to compute this problem here, right? I have the Bregman divergence here. I have this Fenchel dual here. And in fact, if you just write down the this update here, and you can show that it actually exactly translates. The U update exactly translates to the update because U is in the dual space. It actually translates to the update in the gradient, right? So this is just an equivalent reformulation, or like if you just rewrite these 3 updates, it's going to give you this. Okay, and this is exactly just accelerated gradient descent. Okay. And so this, so this is also like you add some negative momentum, right, to your gradient, and then you update your x, right, with this gradient term. Either you add some convex combination steps for those 2 iterations. So this gain perspective of accelerated gradient descent is not really new, right? This was first, I think, identified by George Lan in 2018, right? So our kind of analysis is slightly different from theirs by just this extrapolation step. There was an order, you can do extrapolation on x or extrapolation on mu, right? There's just slight variation there, but elsewise it's the same, okay? So there's, again, nothing new here, okay? So now you can see that we can use Primal-Dual to handle bilinear problem. We can use Primal-Dual to handle smooth terms. And then if you have those this original problem we have in mind, and natural idea is let's just try to run Primal-Dual here, right? And let's first, as we did before, rewrite this f of x and lift it to the dual. Okay, we're maximizing over mu, right? We just rewrite this f of x by maximize this part here. Similarly, we do it for h, right? We lift it to the dual space by minimizing over v, right? This is the dual for that. Okay. And this part remains remains the same. Right? And if you yes. Sure, yeah. So minimize f of x is equivalent to maximize over u of this term. Right, so I'm just rewriting f of x as a maximum over u and this. And then I'm rewriting h of y as minimizing v of this. Right, so I can switch Minimax because here there's the strong duality because it's Strongly-Convex-Concave, compact, like well-defined closed convex sets. Yeah. So the orders doesn't really matter. That's why I'm merging them here, right? Just minimize over xv instead of writing as Minimax. So it's basically the dual of this Minimax optimization problem. So the dual of Minimax is going to be still Minimax. Okay. So a nice feature of this reformulation, right, is that if you look at this reformulation, you can see that they're all simple terms, right? So this is the differential dual of f under 9. This is a very simple term. You can easily handle it as before. This quadratic term is simple, right? Simple, and this term is also simple. And then you only have those bilinear structure here. Okay. So there is only bilinear structure plus a bunch of proximal friendly terms. Okay. And you can just apply Primal-Dual algorithm to solve it, right? So if you apply the Primal-Dual algorithm to solve it, right, it's just the extrapolation steps on your variables, right? You just throw it the gradient here, and you Bregman divergence here, right? And then those simple terms, you just keep it intact in the subproblems, right? So this is Primal-Dual algorithm. Of course, similarly as before, you can see that this when you use this Bregman divergence to update U, those are basically equivalent to just updating on the dual space, which is updating the gradients. Okay, so basically what you have, like this is equivalent reformulation, or translating that is basically you update your X, right? With these extrapolation steps, right? You update your gradient for both X and Y, right? And then you plug in your gradient and update the X and Y, and then you do some other convex combinations of previous iterations. Okay, everything is basically similar as before, except we have an extended space, not just X and Y, but X, Y, and UV. Okay, and if you do this, right, so you can analyze it very easily, just following kind of similar analysis of the original Primal-Dual algorithm, and you can show that actually this algorithm converges linearly. And it converges linearly with this exponential decay rate that relates to kappa. And kappa is exactly equal to this, this term here, what I define here, right? And to translate that, this basically means that the gradient complexity you need is basically of this order, which exactly matches the lower bound we see before. Okay, so shouldn't come up as much of a surprise here, right? Yeah.
This algorithm is in the class before.
Yes.
Okay. Can you comment on that?
Right, because as I said, you can reformulate this as this, and you see that you only need gradient updates here. So it's first order methods, yeah. And I should also mention that the lower bound that people come up with here, this applies to first order methods. That includes single loop, multiple loop algorithms, okay? at this point? All right. So this seems to be like the end of the story, right? We're able to close, the gap and match with the lower bound exactly. Of course, the next thing you might be wondering is, what about, if you don't have strong convexity on both sides? Let's say if your objective is convex on one side, but strongly concave on the other side, right? So you can like what Mason discussed yesterday, right? You can add this of order epsilon quadratic term to your objective, make it strongly convex, strongly concave, right? That corresponds to basically you have now strongly convex, strongly concave objective with mu x equal to of order epsilon, right? If you just plug in this order epsilon term into this lower bound here, right, to replace mu x by epsilon, this mu x by epsilon, right? This is what you will get, right? The complexity. And this complexity is basically nearly optimal, right? You can see this component, because you're dealing with a smooth minimization problem, this is the best you can hope for. This other term here, you're dealing with the bilinear structure with strongly, but this is also the best you can hope for, right? This logarithmic term 1 over epsilon times this condition number is the best complexity you can get for solving a strongly concave minimization problem, right? So each of those terms are optimal, right? I said it's near optimal because this 1 over epsilon has this addition logarithmic 1 over epsilon here, right? This logarithmic should really only appear for this condition number, not these other two, okay? And this is also the best, I think this is best known result in the literature. If you, of course, you might say, I don't really want to use smoothing because I have to choose what is this mu x, right? It's not, it requires some tuning. You can actually just apply the same algorithm I discussed before, lifted Primal-Dual algorithm, by just, instead of using a constant step size, you can use some decaying step size instead, just like what you do in the convex concave settings. And then you can show that it actually gives this 1 over t square convergence rate. And that leads to the following gradient complexity, right? Which is, again, dominating term is of order 1 over square root of epsilon, which is the best you can hope for, right? And so you basically get 1 over square root of epsilon for each of those terms, right? So it is not as good as this one, as you can see, right? Because this one, for this condition number on the y component, you are supposed to get linear convergence rate log 1 over epsilon, but you get this 1 over square root of epsilon here. If you recall what I discussed in the talk I gave before, like you can get this 1 over square root of epsilon term also with log 1 over epsilon by just using catalyst plus extra gradient for OGDA. Right, this is strictly worse than this one. If you look at the dependence on this Lipschitz smoothness term, okay. And I should note that these two complexity bounds are the best known among all of the algorithms known so far. And the reason why these are best is really because like we're able to close this gap and get the optimal dependence here at first place. All right. So just a quick summary here, like we're able to actually design single loop, optimal algorithm for solving bilinearly coupled Minimax problems with strong convexity on both sides. I mentioned earlier there was a work by Yujia and Aaron and Kevin that they were able to further, relax this to generally coupled, like general coupling instead of just bilinear coupling, right? Of course, the intriguing question is, are we able to further extend this to more general Minimax optimization problem without having to separate fx and hy out of your objective, right? Just arbitrary phi of xy. So this remains an unknown, an open question there. And can we extend this to, we've shown we can extend the results to other settings like strongly convex concave or convex strongly concave, but can we extend it to non-convex settings, right? One idea, of course, if you use the catalyst or those other acceleration mechanisms or smoothing mechanisms, you will be able to get good results for these other settings, but you will end up with having at least 2 loops instead of 1 loop. So whether you can, further reduce, further modify the algorithm to make, to get a single loop algorithm to achieve optimal rates on those settings is still unknown. And also, how can we generalize those to, stochastic or finite sum settings? So I think there are, in general, lots of really interesting open questions there that can be done. Okay.
What is the finite sum?
Finite sum is basically objective. It's like just 1 over n summation of n different components. Yeah.
Thank you very much. Any questions for Niao?
Yes.
Make it work.
Thank you, Niao, for the great talk. Yeah, first of all, the idea is very nice and very simple. Any clue on whether you could extend the same techniques, or like there is no hope to do similar things
To other settings?
To yeah, non-separable, let's say.
To non-separable case.
Any of these questions, could you use a similar idea?
Yeah, for this non-separable one, I'm not sure. I think the Primal-Dual approach cannot be easily extended to, in general, like the general min-max optimization problem. Like the Primal-Dual are really optimal when you have this bilinear structure, but beyond the bilinear structure, those are not always the optimal algorithm. Right. So here there's a question mark here. Is this lifting idea the best thing to do? It's possible, right? Because you can still lift, you can still have like dual formulation of min-max problems, not necessarily bilinear, but it's more like you have to design what is a conjugate of, in general, like a min-max optimization. So there's a lot of sophistication there. I say it's not that straightforward. But this other, I think the other technique in Yuja and the other work, they were using something more like relative Lipschitzness. Those are a bit more general than this Primal-Dual perspective. Yeah. And your answer to these other settings, the answer is yes. I didn't have time to cover my second part, but you can actually propose very simple like Primal-Dual type methods, and you can deal with like stochastic settings and even settings without strong concavities, and you'll be able to show like much better improved, dependence on condition numbers for these settings comparing to existing method. Like this is, I think, what Mason talked about yesterday, right? Where you have this GD max type of methods, which has much higher dependence on condition numbers, but you can actually get much better dependence on condition number with this like simple single loop algorithm using some of these Primal-Dual ideas. Also in the stochastic setting, you can get kind of the best dependence on condition numbers without really having to go through two loop algorithms. So it's possible for many other settings, but not necessarily, the very general one. Yeah. Yes.
Thank you a lot. That's a very nice talk. I was wondering a little bit for the non-convex setting, because I'm not very familiar in that case. I wonder if there are any non-single loop algorithms for these settings and what the ideas is based on.
Right. So for instance, so here we can look at like say general stochastic optimization problem, which is non-convex in X. But it is also not necessarily non-concave in Y. And so here I'm considering, for instance, like problems that satisfying the PL condition here for the Y component. Right? This does not necessarily require anything like concavity or strong concavity in Y. Right? You can have single loop algorithms to solve it. Right? I had this maybe a summary here. Maybe this one. Right, if you like, this is non-convex objective, right? If you just apply stochastic gradient descent ascent, you would expect it to have some complex like epsilon -4, and with like cubic dependence on condition number. And that requires you to also use very large batch sizes at every iteration to estimate the gradient. If you don't use large batch, there was a work, I think this is work by Tian-Yi Lin and Chu Jin and Michael Jordan, right? They've shown that if you don't use a mini batch, you get worse complexity like epsilon -5. But what we've shown that you actually, you don't need a mini batch. You don't need two loop. You can have a single loop algorithm, right? That achieves this epsilon -4 with much smaller dependence on kappa. And without even requiring anything like strong concavity of that, yeah.
What is the framework of the algorithm?
So the framework of the algorithm is also very similar to this Primal-Dual, right? Except that you are not using the true gradient. Here is just an unbiased gradient here. And then there was also some like extrapolation steps, yeah.
Thank you.
And actually, I didn't show the numerical results, right? This is basically what everyone will play with Wasserstein GAMs for this type of problems. Here, let's say you have a non-convex strongly concave problem. I'm using just a neural network for the generator, but just quadratic discriminator here. So I think yesterday, Gaussier has talked about like the performance of Adam, right? So here, what we observe that, yes, in general, Adam performs better than, just running gradient descent ascent, okay? But we've shown that if you have this, slight modification of this gradient descent ascent with this alternating structure and with this smoothing, then you can actually get even better performance than Adam. It doesn't really require a lot of tuning or anything, right? So there's also like a lot of promise on the numerical side of these single loop algorithms. Yeah. All right, I think I have all the references here, and if you're interested to look into some of the details, feel free to send me an email, and I'm happy to share the slides. Yeah. Yes.
So for the non-convex concave, if you apply your algorithm, sorry.
Mm-hmm.
For non-convex concave, if you apply your algorithm, you get optimal rate by 2 loops, right?
First of all, we don't know the optimal rate yet in the non-convex concave set.
No, I mean the best node. You get the best
You
node.
get the best node.
You get the best node.
With a two-loop algorithm.
With 2 loop, yeah, you get the
number.
best node and then the 2 loop. But okay. Are there any other algorithms that they can do 2 loops? As far as I know,
No.
they can get because the other ones are works. Some other works are 3 or 4 loops.
Right, like
Most
the
of them.
one that I mentioned here, I think by I did mention here. I think I have it maybe here.
Yeah.
So this work requires 3 loops, right? This work requires 3 or maybe 4 loops in order to get this one or epsilon -3. And they have a very high order of logarithmic dependence for logarithmic terms here. And I think you can use the trick, right, to improve these results, mostly on the condition, mostly on the dependence on those matrix part. The epsilon part you cannot really do much, but you can get rid of those logarithmic terms.
All right.
So the catalyst framework, or frameworks of this type, I wonder, like, they have 2 loops, but like, is there a generic at least, approach to just do 2 time scale methods to say, okay, it's 1 loop, but like,
Right. Exactly, right. So this one, I didn't go into the details here, but this is like exactly like you just run 1 step of the catalyst. So like the sub problems originally would use multiple steps to solve it to some accuracy, but you can just in some settings you can just afford just 1 step instead of multiple steps, because the sub problems are strongly convex, strongly concave. So running for constant number of steps gives you comparable performance as running for like logarithmic 1 or epsilon number of iterations. So in many cases, you can just reduce it directly to a single loop. But yeah, so our analysis, we will only analyze for several cases. It's not like every of these settings you can do this reduction there. I show it here. Yeah, I have an additional slide. Is like the algorithm that I talked earlier, that for loop algorithm that gets you there. As you can see, it's fairly complicated there. I didn't put it in my stuff. Yeah, I think in general for all these other settings, it's possible to, improve the catalyst to make it just one loop. But there is some sophisticated analysis that you need. If you don't care about the addition logarithmic factor, that's fine. But if you care about this logarithmic factor, then you have to use a lot of techniques like warm starting, like the way, and also maybe some other techniques to get rid of those additional logarithmic terms. Yeah. All right, thanks for the questions. Yeah, happy to talk more offline.
Thanks again.